Okay, today we're going to be looking more deeply into the multiplication law and application of the multiplication law. So let's quickly just revise what the multiplication law is. The multiplication law says that if the probability of A and B is equal to the probability of A multiplied by the probability of B. But this is only for independent events. And in set notation we write that as the probability of A and B is equal to the probability of A times the probability of B. And we can use this for more than one event, so we could have the probability of A and B and C and so on and so forth is equal to the probability of A times the probability of B times the probability of C and so on and so forth. Because this only works for independent events, if we can show that the probability of A and B happening is equal to the probability of A times the probability of B, then we can prove that A and B are independent. So let's look at a couple of examples to show this. So events J, K and L are independent. So we're not showing that they are, we're told that they actually are independent. So given the probability of J is equal to 0.5 and the probability of K is equal to 0.6 and the probability of J and L is equal to 0.24, we want to find the following. Firstly, the probability of J and K, then we want to find the probability of L, and then we want to find the probability of K and L. So let's find the probability of J and, oops, daisy, don't need that there. J and K is equal to the probability of J times the probability of K. We're given the probability of J is 0.5. Probability of K we're told is 0.6, and that gives the probability of 0.3. Now I want to find the probability of L. Now we know that the probability of K and L, which is equal to the probability of K multiplied by the probability of L, is equal to 0. Well, it says what we want to find out. No, sorry. We know the probability of J and L. That's what we want to find out at the end. So J, probability of J and L. So probability of J is of J and L together is 0.24, and the probability of J is 0.5, and the probability of L is what we want. So just rearranging the formula, we get the probability of L is going to be 0.24 over 0.5, which is 0.48. And finally, we want to find the probability of K. Oops. And L. So it's the probability of K times the probability of L. Probability of K is 0.6 times the probability of L, which we've just worked out is 0.48. So that gives 0.288. Now, let's consider some examples of independent events. And these are not always at first clear. We can prove there. It's easier to sometimes prove by looking at the maths than intuitively thinking about the situation. So that we're going to look at some examples of independent events and non-independent events. So firstly, enjoyment of sport is independent of gender if equal proportions of males and females enjoy sport. If unequal proportions of employed and unemployed people own cars, then car ownership is not dependent on employment status. It's dependent. Now, we're going to look at an example that explores this a bit more deeply, and you'll see from the example it's not at first clear if the event is dependent or independent, but the maths will make it clear to us. So in a group of 60 students, 27 are male. And we're going to denote maleness by M. And in this group of 60 students, 20 students study history, which we'll denote H. So we've got this Venn diagram. So this is our group of 60 students. And in our Venn diagrams we're shown this is our male part, and we have 20, and we're shown that we've got 18, and this is for history. 9 of those male students study history and 18 don't. And we know that in this history we've told that there's 11 plus 9 is 20, so that is our history set. And then we've got 22 students who are not male and who don't study history. So this here, the male bit is, those that are male make up 27, those that study history make up 20. Now we're given this. One student is selected at random. Show that the events a male selected and a student who's studying history are independent. So we know that if the events are independent, then the probability of being a male and the probability of studying history multiplied by the probability of studying history is going to be equal to the probability of male and studying history. So we're using the multiplication law to prove the independence of these two events. So let's firstly find out the probability of being a male. So we're told there are 27 males out of 60 students, and the probability of somebody studying history, we're told there are 20 history students and 60 are out of the 60 students. So the probability of being male and studying history is going to be the probability of being male times the probability of studying history, which is 27 over 60 times 20. That's a very bad 7. 20 over 60, and that will give us, working all that out, you'll get 9 over 60. Now, oh, sorry. We don't know the probability of being male and history. So the probability of male times the probability of studying history is that. Now, what is the probability of being a male studying history? Now, we have to look at our Venn diagram for that. So if you're male and you study history, you are in this middle section here. So there's nine males studying history out of the 60, which is the same as that. So the multiplication law holds, and therefore the events are independent.